Hello, and welcome to Agrosive Physics. Today is day 129, and what we're going to discuss today is the duality of light. Now, the duality of light states that light has both wave and particle properties. In some instances, it acts as a wave, and in other instances, it acts as a particle. Now, the wave theory is what we discussed when we talked about the light chapter. And when light acts as a wave, it experiences the following types of phenomena. Light can be reflected. Light can be refracted. Light can also be diffracted. Those were all proof that light acted as a wave. And we went through each of those sections specifically on how light did that. Light was able to bounce off of a mirror. Light was able to go through a material medium and change speed, so it was refracted just like any other wave can do. It also goes through a double slit diffraction film and experiences interference on the other side. So the fact that it diffracts and interferes proves that light is a wave. Now, if we remember back from the light chapter, light had a specific speed. It was the speed of light, and it was 3 times 10 to the 8 meters per second. In a material medium, it slows down, and we were able to use the index of refraction in order to determine how much light slowed down. The bigger the number for n, the lower the value of the speed in the material. We also had the fact that we could calculate the frequency or the wavelength of the light based on the equation V equals F lambda. That's the wave equation. So light is, as far as those are concerned, a wave. Now, Newton did not believe that light was a wave. Light was a particle as far as Newton was concerned. Unfortunately, it was just a hunch. So Newton didn't have the capabilities of determining that light was indeed a particle. Now, light was a wave for his contemporaries, and he understood that light was a wave, but he also believed that light could act as a particle. And he thought of light as a packet of little bits of waves that acted as particles, and he called those photons. And photons would have momentum, and they would be able to interact with other objects, hit into them, and exert energy similar to how particles act. Now, of course, we know that light has no mass. So the fact that Newton thought that light was a particle, he wasn't able to use the equations that particles exhibit. For example, you couldn't do 1/2 mv squared for the kinetic energy of light because it didn't have mass. So the equation didn't work. He also couldn't find the momentum because P equals mv doesn't work if you have mass of 0. So he was unable to prove that light was a particle. Fortunately, in the 1900s, scientists were able to show how light behaved as a particle. Light is a wave. We've proven that. But light also is a particle. And in the 1900s, that's when we were able to determine the fact that light could act as a photon, as a bundle of light beams, and actually exert energy onto objects similar to how particles act. Now, since we can't do 1/2 mv squared, we found a new equation that relates Planck's constant and allows us to figure out the energy of a wave. Now, Planck's constant is a value that shows that light exists in discrete amounts of quanta, which is the amount of energy that light has. And this value is 6.63 times 10 to the negative 34 joule seconds. And Planck is the one who came up with this. Now, if we use that constant, we have an equation that allows us to find the energy of a photon. And we can do E equals hf, Planck's constant times the frequency. Or if we rearrange it using V equals F lambda, we can figure out the energy of a photon of light using hc over lambda. So, what does that mean? It means that high frequency light waves exert more energy than low frequency light waves. So higher energy is exhibited in higher frequencies. For example, gamma radiation has a much higher amount of energy than visible light, let's say. Now, that being said, the wavelength is indirectly related to the energy. So small wavelengths show high energy, and gamma radiation has a really small wavelength. So we have this principle that shows that light is a particle, and it's based on what we call the photoelectric effect. We're going to discuss the photoelectric effect in tomorrow's lesson. But for today, Newton was proven correct in the 1900s. So he had to, well, he didn't have to wait because he had passed away, but we had to wait as a scientific community over about 200 years before we were able to verify that Newton's hunch was accurate. So at this point, what I'd like to do is calculate the energy of different types of light waves. We'll take out the whiteboard and we'll calculate the energy of, let's say, X-rays, invisible, and maybe gamma radiation. We can use Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds, and multiply it by the frequency, or multiply it by the speed of light and then divide it by the wavelength. Either way, we're going to find the energy of photons in joules. That's it for today. Let's take out the whiteboard now and do some sample problems. Thank you. Now, earlier in the course, we talked about light as a wave. And the way we proved that light was a wave is that it reflected, it refracted, and it diffracted. Now, Newton didn't believe that light was a wave. He thought it was a particle. And he wasn't able to prove that it was a particle during his lifetime. He had a hunch. But since he wasn't able to prove it, we couldn't verify. So, fast forward a couple of hundred years, and we were able to verify that light does act like a particle as well. So we have these photons, which are bundles of light rays. And when they interact with different objects, they will interact just as particles do. Now we have an equation that allows us to determine that, and that's E equals hf. Now, if we don't have the frequency, we could use the alternative version of that, which is hc over lambda. So the energy of the wave is related to the frequency or the wavelength. Now, the way we can use this in a calculation is we can calculate how much energy is present in the photon if we know its frequency in hertz or the wavelength in meters. But we also need to know this term h, and that's Planck's constant. And Planck's constant is 6.636 times 10 to the negative 34 joule seconds. What we'll do now is we'll calculate the energy of different wavelengths of light. Now, in order to find the energy of the photons, we're going to find the difference between red and violet and see which one's more energetic. Now, the equation is hf or hc over lambda. And since we have the wavelengths in this case, we're going to use the second version. So E equals hc over lambda. So h, 6.636 times 10 to the negative 34 joule seconds. C is the speed of light, 3 times 10 to the 8 meters per second. And that's all over. For red, we'll use 750 nanometers. Now, instead of nano, let's just convert it right now, times 10 to the negative 9 meters. All right, 6.636 E negative 34 times 3E8 divided by 750 E negative 9. And we get the energy to be 2.6544 times 10 to the negative 19 joules. Now, in order to find the energy of the violet light, we do the same equation, but instead of 750, we use 400. So 6.636 E negative 34 times 3E8 divided by 400 E negative 9. And we get 4.977 times 10 to the negative 19 joules. So, violet versus red. Violet is more energetic. And the way we can think about this, since wavelength is indirectly related to energy, the lower the wavelength, the higher the energy. Now, since frequency is directly related, the higher frequency waves will have more energy. And typically people like to remember the frequency because that's how our reference table is listed. It lists from low to high frequencies. So gamma radiation is going to be all the way on the right, and that is the most energetic of the forms of light. But in this case, in terms of visible light, red is going to be less energetic than violet. Violet has more energy because it has a higher frequency.